Now in this, not so much this session, but this board, so the next 4 sessions, I think you'll begin to get a feel for why I've been saying that theory of computation, this course particularly, gets quite pure mathsy, has a feel about it of being very pure math, because by the time you get to the fourth session in this board, you will get that feeling. I mean, we will see for the first time not a theorem statement, we've seen that before, but the first real theorem in the sense of theorem statement, and the theorem itself, like the proof of the theorem itself, is complicated enough that Sipser, the author of this text, feels that it's a good idea to provide a kind of preliminary outline on the direction and the nature of the proof, so which he just calls simply a proof idea, the idea of the proof, the main features of the proof. So we will have our first such theorem with its proof, well, with its proof idea, and then the detailed proof. Well, we'll start with the proof idea. We won't get to the proof, the detailed proof, the actual proof, until the next board, so several, 4 sessions away. But we're getting there, and when that happens, I would say we are leaving behind the junior level and moving up into senior level. And when we get into, well, there are 2 chapters in the text. Let me just check. I think they're chapters 6 and 10. Let me just check. And both of them, 6 and 10, they both, the chapter titles started with the words Advanced Topics in. So chapter 6 is Advanced Topics in Computability Theory, and chapter 10, which is the last chapter in the book, Advanced Topics in Complexity Theory. Now, both of those chapters, I would say, are M1 level, because they're harder again. Now, I've warned you about this. Now, I'm not quite sure if that's the right word, warning. If you don't like pure math particularly, then the word warning is appropriate. If you love pure math, if you have a sort of pure math type mind, if you're a sort of mathy person, then theory of computation you'll probably like very much. So now if you're sort of like me, you're a math physics type person, like you love math for its own sake, but you also love physics because you're curious about the world. You want to know how the world works. And for some weird reason that's very deep and metaphysical and has religious overtones almost, is that the world obeys very mathematical principles. So if, like I keep saying, I'm open to deism, I'm suspicious our universe has been designed by some hyper-intelligence. I'm the guy predicting the Lect war, right? If you don't know what I'm talking about, have a look at my website. But I'm the guy who's saying that a major war is coming that will kill billions of people over the issue of species dominance. In other words, should humanity this century build artilects, one of my words means an artificial intellect. In other words, a godlike, massively intelligent machine, which would have mental capacities, well, looking at the physics, trillions of times above the human level, and hugely more if we make these creatures have quantum computing. So it's plausible then, if these creatures come into being, they may become so massively intelligent, they may be able to conceive and design and maybe actually build universes. So for all we know, given out there trillion stars, and most of them are billions of years older than ours. So maybe these kinds of Artilect type creatures have been around for ages, and maybe they built the universe that we live in, giving it the properties that we now, as scientists, are discovering and learning about. It's plausible, right? Anyway, so so if you're like me and you love math and you love physics, then I think you'll like this course more and more as we get into it, because it is very mathsy. And it's about computation. It's about what can you compute? Like, what are the limitations of these computing machines? Like these Artilects, if we build them, will they be subject to the same kinds of limitations? Like, are our own minds, our own brains, are they also constrained in the same kinds of ways that computers, machines are constrained? These are fascinating philosophical, even metaphysical questions, right? That you can really get into when you study these kinds of stuff. Limits of computation. What can machine minds, like what can artificial intelligence do? What are its capabilities and its limitations? It's a fascinating subject. Okay, I hope you'll pick that up as we get into it more and more. Especially if, well, not if, I will. I'll give like an extra course link to this one on Gödel, and tied up with Turing. The Gödel and Turing, they're closely linked. And about theorems, one thing I must do, I went to the end of each chapter. I wanted to list the number of theorems in the whole book. My estimate was that it might be hundreds. And it dawned on me that Sipser he uses what I call global ordering. Global ordering. And what I mean by that is, like in a chapter, you'll have definition, example, lemma, proof, corollary, and so on, and a whole mix of them. And he just labels them in the order in which they appear. So it might be like 1 is a corollary, and 2 might be an example, and 3 might be another example, and 4, and so on. So so when I went to the end of the chapter and looked at the number, the ID, the number of the last theorem in the chapter, thinking that would be the number of theorems in that chapter. But no, he uses global ordering. So mixed up in that, let's say the last number was 44. So initially I'm thinking, 44 theorems in that chapter. But no, because that 44 somethings include examples and things other than theorems. So I had to go back to the drawing board. So I now realise it's going to take me quite a bit of time. I'll have to systematically go through each chapter and just count the number of theorems in that chapter to get the total in the whole book. So I'm curious. I want to know, like, how many actual theorems, full-blown theorems, are there in this text? Because my feeling is there's quite a lot. My guess is somewhere maybe 10, 15 per chapter, maybe. So over 100 theorems. That's just my guess. So it's something I will do in the next day or so I can report back to you what the result will be. So this board, not this session, but this board, we will start on our first serious theorem, requiring, according to Sipser, a proof idea, because the proof itself is fairly complicated. So you need a sort of overview to start with on how it works. And this pattern of his, theorem statement, theorem idea, and then the actual, proof idea, and then the actual detailed proof. Okay, so that's leading. Now, we were talking last time about our first concrete example of constructing, actually designing an automaton. And the task, or the language if you like, the language of the automaton is all those strings that have an odd number of ones in the string. And the string is assumed to be a binary string. Okay, so the alphabet is just a set of 0 and 1. Okay, and we got as far as concluding that we'd have two states.